All right. Well, you are with me again. I am Mr. Hein. We're looking at curve analysis, the final part, putting it all together. But we're going to look at this function fx equals x to the third minus 27x and fully investigate it, find all its critical points, find its local maximum, minimum, any points of inflection, any concavity. All right. So let's see what happens. So what we want to do is, given if fx equals x to the minus 27x, we want to find when is it increasing. We want to find when is it decreasing. We want to determine any local maximums, any local minimums. Let's see if there's any points of inflection. And let's do any concavity. So when is it concave up and when is it concave down? So quite a bit we want to understand about f of x. And now we're going to do this through all the definitions we understand. We're going to do it mostly through the algebra. The last video I did was through the graphical perspective. This one's really through the algebra. Right? So if fx equals x to the minus 27x, then the derivative of f will be 3x squared minus 27. And the second derivative will equal 6x. Okay. So let's see here. So when is f of x increasing? So fx is increasing when f prime of x is positive. So this one, we're going to look at f prime of x, which is equal to 3x squared minus 27. And we want to look at when is it positive and negative. So let's find the zeros of it. And the zeros of this, if you add 27 over, you get x squared equals 9. So the zeros of this are 3 and negative 3. And I always like to make number lines to help make sense of this. So f prime of x. And we have at 3, and we have at negative 3 are its zeros. So remember that these are its critical points. F of x is critical points because since f prime of x equals 0. Okay. So now we want to determine if there's positive, negative in each of these intervals. So before negative 3, let's say negative 4. And let's do like negative 100, because it's anything on this side. Negative 100 squared would be positive, a really large number. Minus 27 will still be positive, so that's positive. Any number between negative 3 and 3, so if I pick 0, 0 would make that all go away, be left with a negative 27. And pick a really positive number, similar thing will happen over here, where a positive number will make that all positive. Minus 27 won't affect it, so it'll end positive. So what we know from this is that that implies that f of x is increasing on negative infinity to negative 3 and from 3 to infinity, since f prime of x is positive on those intervals. And we also from this know that f of x is decreasing from negative 3 to 3, since its derivative, its slope function, is negative on that interval. What else does this tell us? This also tells us that f of x has a, so at negative 3, the slope function is going from positive to negative. So it has a positive slope, and then it's becoming negative. So that's a local maximum. So x has a local maximum at x equals negative 3. And f of x has a, I'm sure it's all showing up, has a local minimum at x equals 3, because it's, what's my reasoning? Since f prime of x goes from positive to negative, and since f has a minimum, since the derivative goes from negative to positive. Okay. Hopefully you can see that a little bit, which is good. So we're putting it together. If you want to find the local maximum at -3, make sure you plug -3 back into f of x. So let's see what that maximum is right away. So at -3, what's f of -3? Well, that would be, you plug in -3. -3 times to the third power would be -27. I'll use my calculator here. -27 minus 27 times -3. So at -3 comma 54 is its maximum, and its minimum will be at 3 comma f of 3, which is 27 minus 27 times 3, which would be at -54. Okay, so that's good to know. Some information that'll be helpful to us. So we did increasing, we did decreasing, maximum, minimum. Now we get the points of inflection and concavity, which all has to do with the second derivative, right? Which I'll use red for. So these three all have to do with f. Double prime of x. All of these have to do with the first derivative of it, f prime of x. So points of inflection. So let's look at the function algebraically. So f double prime of x is equal to 6x. Let's find its zeros. So f double prime of x, we know that it'll equal 0 at x equals 0. F double prime of 0 will equal 0. 6x equals 0 then. Now, is that a point of inflection? Now, remember, point of inflection means it has to change signs. So what's happening to the negative? Well, 6 times a negative number would be negative, and 6 times a positive would be positive. So that, in fact, at x equals 0 is a point of inflection, since f double prime of x changes sign. Okay, and that's good. And then, so there's a point of inflection at 0, comma, if I plug 0 back into the function up here, it'd be at 0. So at 0, 0, there's a point of inflection. So if you lost what I did so quickly at 0, comma, f of 0, if you plug that in. And when is it concave up? Well, it's concave up from 0 to infinity, since f double prime of x is positive. And it's concave down from negative infinity to 0, since f double prime of x is negative on that interval. So if we put it all together, let's see what this graph looks like. Right. I'm going to zoom out so we can see all of this all together with the graph at the bottom. So let's see f of x. All right, so we knew that it had a maximum at -354. So -1, 2, 3. Somewhere up here, I'll just mark -354. It had a maximum. And it had a minimum at 3, -54. So 3, somewhere down here, which we'll just mark 3, -54. It had a local minimum. Okay. And then it was, what else did we find? Is that its critical points are at -3 and 3, which we know that because the slope is 0 at those points as it changes sign. And at 0, 0 was a point of inflection. So that's when it's got to change from concave down to concave up. And I think that might be all we need here. And it's increasing from -3 to -3. So we just start to connect this. Increasing from there to there and from 3 to infinity has positive slope, and it's decreasing from -3 to 3. So all of that is decreasing, like so. And I think that covers all of it. And you can see the concavity from 0 to infinity, it's concave up. So all of this right here is its concave up. And notice how it's holding water. And then it's concave down from -infinity to -0, which you can see it has the shape of where it's losing water. And that is concave down. And just like that, we used everything we know about rates of change from an algebra perspective to put together the graph of f of x, which has very big implications. Is we can figure out a function f of x, which can represent an amount of something, just knowing its rates of change and what's happening at its rate of change. So again, say what's something that's changing. Say we know how fast you're filling up a water bottle, and you want to just knowing the rate at which it's filling up and the rate at which that's changing, we could figure out so much about just the amount of water that's getting filled up. All right. So there it is, curve analysis, all of these keywords through an algebra and graphical approach. I hope that helps you. If not, you can always reach out to me and your peers in the class. All right, good luck with that, everybody.